All right, this section is 9.5, Parametric Equations. This is kind of its own little one-off section. There's no real good spot to put it. Um, so you can graph conics and things with it. So there's the section with conic sections on it. Makes as good a sense as any. So, but parametric equations are just another way of looking at graphs in the plane. So suppose that t is a number in an interval I. A plane curve, that doesn't look very good, does it? Plane curve is a set of ordered pairs x, y, where x equals f of t, y equals g of t for t in an interval I. So it's basically where we have an extra variable called t, which is called a parameter, and then x and y depend on t instead of on each other. And the equations x equals f of t and y equals g of t are called the parametric equations for the curve. So again, it's instead of having y in terms of x, it has x and y both in terms of a third variable called t. Again, the t is called a parameter. And you can actually set your calculator up for this. We'll take a look at that. All right, so graphing a plane curve, basically you're going to select some values of t on that given interval, and then we're going to plug it in to calculate x and y. We're going to plot the points x and y, and then use the arrows between the points to show the orientation of the curve, or the direction if you want. The orientation of the curve corresponding to increasing values of t. All right, so t is between -2 and 2, and we're going to graph where x is equal to t squared plus 1 and y equals to 2t. So this looks like -2, -1, 0, 1, and 2 might be good values. And so let's plug it in for the x. We figure out that the x is 5. -2 times 2 is -4. So our point is 5 and -4. Now we plug in 1, we get 2, -2. Plug in 0, I get 1, 0. Plug in 1, I get 2, 2. Plug in 2, I get 5, 4. So let's go ahead and plot those. So I have 5, -4, 2, -2, 1, 0, 2, 2, 5, 4. So let's connect them. Oh, that didn't work very well. And then we're going to have little arrows to know which way it's going. Notice I'm not going to have arrows on the end of the curve because it is like, even if my graph went on further, if my graph paper went on further, the graph would stop at those spots. So like, just as an example, if I have another point that had these 3 points and that was it, that would be my curve, and I would not have arrows on the ends because we only plot our curve for the values of t that we have. So these are points, these are not arrows on the end. It would be incorrect to have arrows there. So sometimes we can eliminate the parameter. This is really, this section is just getting you used to working with them. You won't really see the benefit of them very much here, but for instance, if you were to actually plot the path of a baseball through the air, it would be much easier to plot it using parametric equations than it would be just trying to find y in terms of x. All right, so sketch the plane curve represented by the parametric equations x equals square root of t and y equals 2t minus 1 by eliminating the parameter. All right, so first off, notice there are no restrictions on t. So basically, in that case, t could be whatever is in the domain of both x and y. So in this case, t must be in 0 to infinity, because I can't take the square root of a negative number, all right? So that's the first thing to recognize. Now, if I want to eliminate the parameter, basically I'm going to get y and get my standard y in terms of x, like we've done before. So if I was looking at this, I'd probably say, oops, let me not write that yet. I have x equals square root of t. I might square both sides. I get x squared equals t. And so I'm going to use that substitution, because t equals x squared. I have y equals 2x squared minus 1. So if I plot that, minus 1, 2, and so it's going to look something like this. And notice as t gets bigger, x gets bigger, so the direction of this curve is here, right? And note, having the arrow on the end of this one is valid because it does go on to infinity. Finding and graphing the rectangular equation of a curve defined parametrically. So let's kind of do this both ways. First, let's eliminate the parameter like the question says, and then let's just do it without and see what happens. So this one's a little bit trickier, but do you agree that if I could look at this and say, well, that's x over 6 equals cosine of t, and y over 4 equals sine of t? Now remember, sine squared of t plus cosine squared of t equals 1, so I could do x squared over 36 plus y squared over 16 must equal 1. All right, so that's an ellipse. So if I were to graph that, I would come over here. I go left and right 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Go up and down 4, and then I'd connect it. All right, so that's not the most beautiful picture, but and then the order that we would go, notice as t increases, basically cosine of t is going to go from 1 to -1, so x is going to go from 6 to -6, etc. So it's going to start here, start at the positive 6, 0, and it's going to go around this way. And then it's going to end there. So let's just see it the other way. Let's let t, let's make a little chart here. X, Y. Let's start at negative pi. Let's go to negative pi over 2. Let's go to 0. Let's go to pi over 2. And let's go to pi. All right, so at negative pi, cosine of negative pi is -1. So I get x is equal to -6. And then y is equal to 0. And then negative pi over 2, that's straight down. So x is 0. Y is -4. Plug in 0, I get x equals 6, y equals 0. Plug in pi over 2, x is 0, y is equal to 4. Plug in pi, I get -6, comma 0. So I'm sorry, I misspoke earlier. In this case, since I was saying we did 0 to 2 pi, but since we started at negative pi, we're starting at this point, and we go around. We still have the right direction, but we start and end at this point, not the one on the right. So finding parametric equations for the function y equals f of x. One thing we can always do is we could let x equal t and then let y equal, basically swap out x for t. But there are infinitely different ways I could choose my parametric equations to represent the same plane curve. So in this case, if I let x equal t, what I'm talking about up here is basically if x equals t, then y is going to equal, just replace x by t squared minus 25. And I'm good. Well, what if x equals t cubed? Well, now this is going to be y equals t cubed squared minus 25. So I'm going to get equals t to the 6th minus 25. Here, if x equals t plus 1, then y is going to equal t plus 1 squared minus 25, which is going to be t squared plus 2t minus 24. If x equals t over 2, then y is going to equal t over 2 squared minus 25, which is t squared over 4 minus 25. Not all choices for x will work. Why can't we start with x equals t squared? Well, what's the difference between all the ones that we've done and x equals t squared? Well, in this case, x can be positive or negative, right? If I do x equals t squared, then x will only be the positive. So all the other ones would give me, the parabola, basically looks like this. And we're down here at negative 25. Well, all the other ones would give me that. If I let x equal t squared, it'll just give me the right half. So x has to attain negative values in this case. All right, so take a few minutes to read the section Advantages of Parametric Equations over Rectangular Equations on pages 1017 and 1018. And as usual, if you have any questions, let me know.